gamma for a bunch of gases. When you increase the degrees of freedom, what happened to the gamma? Did it increase or decrease? It decreased. That's right. So we want low degrees of freedom. Because as the degrees of freedom increase, gamma actually goes down. So let's talk about how these are implemented in the car engine. So first of all, your normal fuel is gasoline. Gasoline are these long carbon chains, right? So how many degrees of freedom do you expect them to have? Just a few or a lot? A lot. So if you really are trying to make a high-performance car, you can use exotic fuels that are not as complicated as your normal gasoline molecule, okay? So you can use exotic fuels which have low degrees of freedom. So that's one thing. But let's say we constrain ourselves to using good old gasoline. So if we do that, we want a large compression ratio. So let's talk about that. I'll go ahead and pull up the diagram again here. Here's my gasoline engine. We walked through all the steps before. And I'll tell you what's, there's always a catch. What would be the problem with the compression ratio being too high? Well, here's the problem, okay? So let's let it go to the intake, okay? So now I've got a gas fuel mixture in here, and I'm about to adiabatically compress it. So we talked about that's the compression stroke. So what happens, I'm compressing it, okay? So I'm compressing it. What's happening in temperature as I compress it? It's going up. Okay. Now, if I had a really large compression ratio, then what I would find is that the temperature would climb a lot, right? If I took these two volumes and I had them be very different, to climb from one volume to the other, right? So climbing temperature, decreasing volume, I've raised the temperature a lot, right? If I have a massive distance of very different volumes, I have a massive compression ratio, I make the temperature climb a lot. And at some point, what would happen is that you'd adiabatically compress this gas fuel mixture so much that it would spontaneously ignite before the spark plug ever got a chance to add any heat. So what would happen here is where this thing is rotating clockwise, right? We're trying to get it to keep rotating clockwise. And at this point, what happened if the stuff just exploded prematurely? It's called pre-ignition. What would happen? It would explode and it would drive the crankshaft back the wrong way. So that's a problem you can have in a car. It's called pre-ignition, okay? So that's going to inherently limit how big of a compression ratio you can use in a gasoline engine. You do not want to actually have such a large compression ratio that you accidentally spontaneously combust the fuel because the temperature goes above the combustion temperature. So if you have some problem with your engine, this is a problem with your, you can go to the mechanic and you can get it taken care of. There's another much more serious problem, which is this. So if it ignites slightly too early, either because of the pre-ignition problem or your spark plug is just timed, what you can do is you can explode this, and what happens is that this tries to just go whoosh and just radially smash the axle, right? So what happens if this gets smashed right through there, okay? That's gonna break the engine. So that's called engine knocking. You may have heard of that, okay? That's a much more serious problem. So it's important to fire at just the right time so that, let's see if I can get a snapshot. You can see right there, the spark plug ignited the fuel when this is just a little few degrees over, so you can keep the crankshaft rotating the same way, okay? So, there's always a catch, right? And the catch for gasoline engines is that your compression ratio can't be too high because you'll have pre-ignition problems, okay? So, there's a couple alternatives that you can use. you can have that when you're adiabatically compressing the gas, or when you're adiabatically compressing the air, there's no fuel there yet. Okay? So let me show you how that looks. Where is it? Here we go. So this is an interesting engine where notice that when it intakes, it's intaking only air. Okay? So then you're adiabatically able to compress the gas however much you want. You're not going to ignite just air by compressing it. So you can operate at much more higher compression ratios. And so what happens here, it just intakes air, okay, right here, and then you adiabatically compress the hell out of it, get it to a very high temperature, and then you don't actually use a spark plug, you just inject the fuel directly and it'll just spontaneously go off because the temperature is so high. Okay, so this is a fuel injector. This is not a spark plug. This is actually spraying in the fuel. This is called a diesel engine, which you may have heard of as well. Okay? So a diesel engine just has a different mechanism to do its thing. Instead of using a spark plug to set off fuel that's already in there, it just injects the fuel. Okay? Now if you compared a diesel engine to a gasoline engine operating off the same compression ratio, the diesel does actually worse. But you shouldn't compare them like that because the whole point of a diesel is that you can run them at much, much larger compression ratios. Okay? Does that make sense? So that's a diesel engine. Okay? Okay. So the next order of business, before I forget, we have to evaluate an engine, not just on the work it can produce, but how fast it can produce that work. Okay? So we should really be talking about the engine power. So what work can it produce per time? Okay? You heard about car engines being rated in this way. Right? You look up this such and such an engine is this many horsepower, right? It's not this can produce this much work. Okay? So let's talk about that. Okay? So let's talk first about that 4-stroke engine that we talked about. Remember that it has 4 strokes. Stroke is basically one trip of the piston from one end to the other. So we talked about there's compression, that's one, and then we have the power stroke, then we have the exhaust and intake. So that's 1, 2, 3, 4 different trips that the piston has to make. Now remember, a stroke is just one way, so this is actually like 2 periods, right? So that's the normal 4-stroke. And so if we were to calculate the power output, it would be the net work divided by the entire period, so I'll use capital T, of the cycle, the thermodynamic cycle. So the power output would be how much net work can we produce when we run this PT cycle once divided by the time it takes for us to do it. So what's the period of our thermodynamic cycle, right? And so here I'm using T for period. Maybe I shouldn't use that because we've been using T for temperature. So this is the just lowercase t, okay? So that's the time to complete one thermodynamic cycle, okay? So here's the problem, is that the net work to complete one thermodynamic cycle, you need 2 periods of the crankshaft to happen, okay? So let me again show you a picture. I know that this is split between today's lecture and the last lecture, so let me really show you. So if you count the strokes here, okay, how long does it take for us to do this, okay? So we have 1, 2, 3, 4, okay? So that's 4 strokes to complete this thermodynamic cycle. So if we can count the crankshaft here, it'll be 1, that's 2, so that's 2 periods of the crankshaft to complete 1 thermodynamic cycle. And if you prefer to see it with the PV diagram, I can of course play this. This is not playing, so I guess forget that. But remember, the way this works is that you have your compression, you have your power stroke, and then you have to do a whole extra thing to do your intake and exhaust. Okay? So it takes longer to complete a net work because you have this whole extra intake and exhaust thing that you have to do. Okay? So let's go over here. Sorry, I have to keep going back and forth. So this factor of 2 is going to mean this thing is not as very high powered because it takes a longer time to make this happen. One of the things I will do is, instead of calling it period, I'll call it frequency. So I'll just flip it. You guys remember frequency is 1 over period. So when this engine is running at so and so many RPM, right? When you hear the engine is RPM, or of course, we would tend to use it in our SI units, okay, which is just hertz. When an engine is running at such and such an RPM, that of course means of the crankshaft. So every 2 rotations of the crankshaft, you complete 1 thermodynamic cycle. And so that's going to be your power output, okay? So for your 4-stroke engine, 4-stroke Otto cycle, your net power output will be net work of 1 cycle times the frequency that you're running the crankshaft at divided by 2, okay? So if you want to find out what is the input of what is the power output of a car engine, you need to figure out how much work is done in 1 thermodynamic cycle and then multiply by the frequency that the crankshaft is running at. Okay? Question?
When you see like on TV and they're talking about the amount of power output, is that number that they say, is that per piston or is that per engine?
Well, this is just 1 piston so
Right.
far, 1 cylinder, so to speak. 1 cylinder. Okay? So if you want the overall, you have to multiply by the number of cylinders. So number of cylinders times the net of 1 cylinder. Okay. So if you hear about a 4-cylinder or 6-cylinder car, 6-cylinder is always more powerful than a 4-cylinder just because you have 6 things doing the same thing instead of just 4. Okay? I guess the net is a better way to put this. This is the power output of 1 cylinder, and then this we could call the net. So let's do it like that. So those are the common things that you hear about when you're talking about car ratings. Okay, what's the total power output of the engine, including all your cylinders? The other thing that you hear is engine capacity. Okay. So engine capacity is another one. What that is just the total maximum volume that you have available. Okay, so that would be the number of cylinders times R times V. Okay, so of course remember that at their largest, when the cylinders are at their largest volume, they're R times V. And then you have, of course, the total number that would have that. Okay. Now, of course, the SI unit with this would be meters cubed. They don't use meters cubed. They use liters. So this is a such many liter engine. Okay. So just so you know, a liter is 10 to the negative third meters cubed. That's typically for car engines. They use liters. For motorcycles, which don't need to be as powerful because they don't weigh as much, you may hear cc's or cubic centimeters. Okay, so and so many cc motorcycle. Okay. Also over here, we would of course use watts, but of course, more typically, this is measured in horsepower, where 1 horsepower is 745.7 watts. So these are the more typical things. You look up your Kelly Blue Book of your car, you're going to find out how many horsepower is the engine, how many cylinders does it have, what's the total engine capacity, and if you look more carefully, you will find that the power output is rated, so this is rated at a particular frequency. Okay, so it can produce so and so much power at so and so many RPMs, because of course that's the frequency right here. Okay, and again, the frequency, we would normally use hertz, but cars usually use RPM, okay, revolutions per minute. So instead of cycles per second, revolutions per cycles per minute, right? So these are all the common things you can look up about cars, okay? You can trace them all back to this stuff right here, okay? So engine capacity, power output, so on and so forth. And of course, the other, just more basic physics 1 thing is like, okay, well, what mass do you have to drag around? You can bet that a truck is going to have a higher horsepower than a tiny little motorcycle, but it also has a lot more mass to drag around, okay? Doesn't mean necessarily that a giant truck is going to beat a motorcycle in a race, okay? So the next point that I wanted to make is that it would be really nice to not have this factor of 2 in the denominator. It just automatically cuts your power of your engine in half. So what if we could, instead of having to do an extra whole exhaust and intake stroke, what if we could kind of condense that all together, okay? So this does exist, it's called a 2-stroke. So a 2-stroke, the power output of 1 cylinder, you don't have that pesky factor of 2 in here, okay? So let me show you an example of a 2-stroke. So we take out 2 strokes, okay? Let's see here. I have a 2-stroke pulled up. There we go. Okay. So here's a 2-stroke engine, okay? And let's carefully take a look at this thing. Slow it down a bit. Okay, so there's your ignition, okay? So let's back up a second. So notice here that you have your, it's just going back and forth, and the spark plug is going off every 2 strokes, not every 4 strokes. So how does this work? Let me show you. Okay, so here, we're about to do the compression, okay? We've got fresh stuff, fresh gas in there. We're about to compress it, okay? And then we'll do the ignition part. So there's the ignition, okay? Now we're going to do the power stroke. So that's our 2nd stroke. And then, rather than a whole trip up and back to do the exhaust and intake, we're just going to go again. We're just going to go again and go straight to the compression stroke. So it's just compression, power stroke, compression stroke, power stroke. That's great, okay? We don't have the extra trip. That's kind of a waste, okay? So what's the problem with this? Well, let's take a look. So here's the ignition, and watch what happens during the power stroke. So here we have, basically, here's our spent fuel, right? We just combusted this. It's going to go out. Here's our exhaust. And we're drawing in the fresh stuff from over here. So watch carefully what happens here. What we're doing is we're actually in the midst of the end of the power stroke, we are simultaneously pushing out exhaust and pulling in fresh gas. Okay, so we don't waste a whole extra trip for that. Okay, so here's the thing though. It would be remarkable, since we're trying to do this all at once, if we got fresh gas air mixture that didn't accidentally go right out the exhaust. Right? We have them both open at the same time. Our intake and exhaust are simultaneously happening. The whole beauty of the 4-stroke, notice here that we are pushing out the exhaust and doing it nice and cleanly. We're pushing out the exhaust, we get rid of it, and then we make sure to draw in the fresh stuff afterwards. So there's no chance of gasoline going wasted out of the exhaust, okay? So gasoline that comes in that is never burned because it just slips right out the exhaust. You can see that we exhaust this, okay? And then we close the exhaust and we pull in the fresh stuff. That is the advantage of doing the exhaust and intake independently, is that you don't accidentally have gas that goes out wasted because it comes in the intake and goes straight out the exhaust and is never actually used in the engine. That's the problem with the 2-stroke. Okay? It would be a miracle, again, if during this stage right here, when we're intaking and exhausting at the same time, if some fresh gasoline didn't just go right out and get wasted. Okay? So that's the disadvantage of the 2-stroke. It's extremely dirty. You know right away if you have a 2-stroke because it's smelly. So an example would be the outboard motor of a motorboat, okay, or a weed whacker. Anytime you're like, what's that smell? Okay, these things are not legal by emission standards to put into cars because they are way too wasteful. There will be some amount of gas that does not get burned. It goes straight out from the intake, straight out to the exhaust. So when are these allowed? They are not for when you have, so getting rid of that factor of 2 is great, but there's an emissions cost. So the emissions cost is too great to put them into things that are like cars. So what you can use them for is when you have things like weed whackers and motorboats, where you have a relatively small engine that you need to be pretty high powered for its size. Okay? So because you can take that factor of 2 out of the denominator, these tend to be very powerful. That doesn't mean you get to put them into a car. It means that you get to make a tiny engine, which is pretty great for its tiny size. Oftentimes because you want the engine to be portable. Like for a weed whacker, you want to be able to carry this thing around, but you don't want it to be super low power. You want it to be pretty high powered for its size. So that's when these things are legal by emission standards. You have a question back there?
Why not like inject a fuel compression phase, like maybe diesel, would that not work?
These are all good ideas. This is there's very, very active research into how to make cleaner burning 2-strokes. It would be awesome to have the best of both worlds. It would be awesome to have a 2-stroke where you didn't have to waste that extra trip up and down, but it would be clean by emission standards. Okay? You'd still have to figure it out. If you injected the fuel here, right, you still have to make sure the exhaust is somehow closed, right? So you'd have to figure out just how you're going to orchestrate this. Let me give you another idea of some people came up with. Here's another example. You can do it like this. So if you actually stare at this for a while, you can figure out that it does complete one thermodynamic cycle for every rotation of the crankshaft, and it does keep the intake and exhaust separate. Any car heads here know what kind of brand of car has this in it? Mazda, that's right. Okay, so this is called a Wankel engine. Okay, so there's lots of good ideas. I think Mazda stopped doing this for a while because there's an inherent technological problems to getting a triangle to rotate inside an oval. Okay, but if you can get it to work pretty well, it has the best of both worlds. You can notice if you stare at it for a while how it manages to keep the intake and exhaust separate, even though it does complete one thermodynamic cycle for every rotation of the crankshaft, not 2 rotations of the crankshaft for every thermodynamic cycle. Question?
Can't you just make the radius of the piston longer and shorten, making the stroke
if you can figure out various tricks to make it work, then yeah, these are all good ideas. Maybe you want to go into automotive engineering. Maybe one day we'll have 2-stroke engines in all of our cars. But right now, they're all 4-stroke, except for when you get to something that's electrical, right? Okay. So maybe that'll be the issue, is that you figure out a perfect 2-stroke engine that's highly efficient, and at that point the electricity technology jumps over it, and then what's the point, right? So that's technology for you. If you're going to be an engineer in the private sector, you got to figure out all that stuff, okay? I'm pulling all these things, by the way, off of this site again called animatedengines.com. There's lots of weird engines that you can take a look at. The only thing I wish it had was the PV diagrams, but there are some really crazy engines, some of which are just for show and some of which have actually been implemented, okay? So there are different ways to run through the PV diagram, okay? And again, they may not all be exactly the same cycle as the auto engine, but for instance, you can go through the same steps that we did for the auto engine, okay? So figure out your heats and your works, figure out the efficiency, blah, 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 okay? Are there any other questions on this? Okay, so there are some questions on the homework. I have you compute this with an actual car. I think it's my car. I can't remember where I got the numbers. It's my Nissan. So it's I can't remember, I think it's 4-cylinder. So I gave it 4-cylinder. I literally looked up in the blue book what is the engine capacity. And you can actually calculate what the horsepower is in my car. And it's pretty accurate, although obviously we're making a few assumptions, okay? So that's a fun little project. I try to make it as realistic to the real world as possible. Okay. So, my next thing that I want to talk about is, okay, I know the efficiency has to be less than 1 because the second law of thermodynamics tells me so. So the question then is, what's the best efficiency I can get? It's not with the auto engine, it's with another engine, or another cycle called the Carnot cycle. Okay? So, what is the most efficient engine possible? Okay, so this is where we talk about the Carnot cycle. So it's a different series of thermodynamic steps. The Otto cycle, this was 2 adiabatic and 2 isochloric. This is not that. This is 2 adiabatic plus 2 isothermal. So it's a different deal. Let's draw it. Looks like this. So the PV diagram would look something like this. Now I'd be following isotherms, and then I'd use adiabatic processes to jump between them. So it would look like this. So, of course, because I've changed the processes a little bit, over here, in the Otto cycle, I had 4 different temperatures on the endpoints, but I had 2 volumes. So I had, in the Otto cycle, I had a high and a low temperature, but I also had 2 intermediate stopping points, okay, that were in the middle, these 2 temperatures. And I had just 2 volumes that I was bouncing back and forth between, and that's what the compression ratio is useful for, is to say how different they are. So this one actually only has 2 temperatures, but it has 4 different volumes. So notice that there's only really 2 temperatures. I'll just call them T high and T low. but there would be 4 distinct volumes here. So 4 distinct volumes, V1, V2, V3, V4, I guess you could call them. So how would you attack this? I'm not going to have a chance to do the play-by-play, but you guys, all you did during homework 7 was learn how to compute heats and works, and so you could figure them out. And then when you put them in here, net work over QH, or let's use the second form, efficiency is 1 plus QL over QH. It turns out, when you work it out, of course, if you worked it out with numbers, you just come out with a number, but if you worked it out symbolically, so again, if you work it out symbolically, you would find that QL over QH comes out to be this. Again, and one of the things that I'm not going to have time for is because we don't have lecture on Fridays to work out the details of how everything works out to that to be the case. So you can try it yourself and let me know if you have any questions. It's probably also in the book because it's a really important cycle. So here we get the efficiency of the Carnot cycle, I'll call it E sub C, is 1 minus TL over TH. So this is actually, we can see, first of all, how might we make this more efficient? If we want a maximum efficiency, what should we do to the T low? Should it be big or small? Small. We want to make this as small as possible. And what about TH? As high as possible. So in order for this to be more efficient, so to improve the efficiency, we want the difference between these two temperatures to be as large as possible. So we want the temperature extremes to be, or temperature differential, I guess is a better word for it, the temperature differential between the high and low to be as large as possible. This is true, by the way, for all engines. It's just easiest to see with the Carnot engine, that if you want an engine to be as efficient as possible, you want to make the temperature extremes larger. So you may wonder why your car engine is so hot. Does it have to be hot? It will be more efficient if it is hot, okay? So T low is going to be just what their low extreme, of course, is your atmospheric temperature. But then you want a temperature that is significantly above that because it's going to make your engine more efficient, okay? So car engines, you want them to have within, of course, reason. You don't want something to melt, but you want T high to be as high as possible. Question?
Does that mean that when we pour in the gas, it should be at like a cool temperature, and then when we compress it, it's going to be hot, and then it's exploded?
That's right, yeah. So the highest temperature we get to, which is we adiabatically compress the fuel and then we ignite it, that is the T, that's T high. Oh, it makes it more efficient if the T high is much, much bigger than T low, okay? So this is, again, we can see it very easily here in the Carnot cycle. This is true of all engines. That improves their efficiency. Now, let's compare this expression to these two weird expressions that I gave you at the beginning. You may be wondering, I gave you 3 different expressions for the efficiency and then really only used the first one as my discussion. Well, the other 2 forms were specifically designed to make it easy to compare to the Carnot cycle, okay? So notice here that I did have T low in one of them, and I did have T high in one of them, but I never got the best of both worlds, okay? I got T low, but then the temperature here is only TB, it's not as high as TH. So this is not going to be as good as the Carnot cycle, okay? because while I got the TL up top, I didn't get the biggest temperature I could get below. I didn't get TH down there, I only got TB, which is only a little higher than TL, right? And likewise over here, I got TH in the denominator, which was good, but the temperature up at the numerator wasn't as low as T low, okay? So it was only this much lower than T high. So clearly these two are not going to be as efficient as the Carnot cycle, okay? So we get the best of both worlds here. We get the lowest temperature in the whole system goes up top, and the highest temperature in the whole system goes on the bottom. So this is going to be more efficient than the Otto cycle. Now, I've only, of course, shown you that it's more efficient than the Otto cycle. I'm here to tell you also it is that you cannot do any better than this. This is the most efficient engine that is possible, okay? So, why is it the most efficient possible? What's that?
Because T low is always constant. We don't go back to T.
Well, so the answer to this is it's a little beyond the scope of the course. I've sort of motivated to you why this is better, but at this point there's no proof that there isn't an extra, you can't get some other term in here, right, that could make it even smaller, right? So the reason why, and again it's a little bit beyond the scope of the course, is that this cycle is heat never flows across a finite temperature difference, okay? So if you're wondering why this is special, it's because this is the only way you can put together a cycle. You never have temperature, or you never have heat flowing from a higher to a lower temperature, which, as we know, is a process that only goes one way, right? Heat always flows from higher to lower temperature and never spontaneously the other way. Well, in this particular engine, heat never flows across a finite temperature difference in the first place. There is never an opportunity to flow from one temperature to another directly. Okay? That is what gives this engine a special place, and in fact, makes it the most efficient engine you can possibly have. Okay? So I'm not going to get into entropy and all this stuff. The other hint you may have about the universality of it is that notice that the only factors that came out in this, there was nothing having to do with the ratio of the volumes or anything. Over here, this was specifically tied to compression ratio and the type of gas you're using. There's none of that here, okay? The only thing that ends up mattering is the temperature extremes that you're operating between, okay? So that hints at the universality. There's no, there's no specific variables on the details of the cycle. Okay. Only thing that ends up being in there are the temperature extremes. So let me try to quickly motivate to you that Q actually never flows across a finite temperature difference. Let me show you a video of the Carnot cycle. So here's the Carnot cycle in action. And so here's the cool thing is that you use the adiabatic processes to jump between the isotherms. And remember, in adiabatic processes, there is no heat flow. So heat can't flow across the finite temperature difference if heat is never flowing in the adiabatic processes. And then, when you get to a given isotherm, notice that there is no temperature difference here at all between the gas and the reservoir. Okay? So you basically use the adiabatic processes to toggle between the two temperatures, and then whenever you're actually in contact with anything, these are exactly the same temperature because it's an isothermal process. So you never have a heat flowing across the finite temperature difference. Okay? So again, I don't want to belabor this point because I know it's a little beyond the scope of the course, so you're going to have to just trust me that the Carnot cycle is the most efficient engine possible. Okay? Question?
So this is just a theoretical engine, right? There's no actual example of it?
Well, you can implement this. I'll talk about why you might not want to. If it's very efficient, then it seems like a good thing. Why don't we all drive Carnot cars? First of all, let me talk about the second law. So the weak form of the second law is that the efficiency has to be less than 1, which is to say you always have to have exhaust. But the strong form is not only does the efficiency have to be smaller than 1, it cannot perform better than a Carnot cycle does across the same temperature difference. Because if the Carnot is the best you can do, that places in an upper limit on that. So the efficiency of an engine can at best be equal to the Carnot cycle, and even the Carnot cycle has to be less than 1. Okay? So again, this is putting an additional constraint, which is to say that you cannot do better than a Carnot cycle running across the same temperature extremes. Okay? So it places an upper limit to your efficiency even that is under 1. Okay? So, a couple things about this. You might point out that you can get this efficiency to be 1 if what is true? If TL is equal to 0. That's right. So there seems to be a loophole here. Okay, the loophole is, what about if TL is 0? What if you run the low temperature off 0 Kelvin? Okay? So this is where we get the third law, which says temperature can't be 0 Kelvin. Okay? So it closes the loophole. You can't get down to 0 Kelvin. Okay? So we'll talk about why that is next time when we talk about fridges, but let me just leave you with this. Why, if this is the Carnot cycle is the most efficient engine possible, why don't we just put it in our automobiles? Well, if we're talking about our power output, the problem is time. It takes forever to implement this cycle because of what? What does it have in it that makes it really annoying? It has 2 isothermal processes which take forever to implement. These are high efficiency, extremely low power applications. You pay for efficiency with very low power. So the efficiency is very high, but the power would be very low because isothermal processes are included in the time it would take to implement. So that's why there's a cost, right? Where our car engines, they're not as efficient as the Carnot cycle, but they're way higher powered and you can get to school on time, okay? So let's leave it there for today. We'll talk about refrigerators on Wednesday.